All right, today we're going to look at logic part 1. And so for the first part, it just wants your opinion. What do you think that logic means, and why do you think we should study it in a math class? So what's the point of all of this? What do you already know? So this is for you to fill in something. If we go down a little bit further, your book defines logic as the study of correct reasoning, often associated with making inferences and the validity of arguments. We're going to be writing a logical statement. A logical statement is one that is either true or false. So we can write a statement below. So I want you to try first. So make sure that you try and write one. Now that you've tried, I'll write an example that I'm kind of thinking of. Again, it has to be a statement that can be marked as either true or false. So if I say the sky is blue, so it is either blue or it is not blue. Compared to if I said something like, go to the store, that would not be a logical statement. Go to the store, because it's not anything, it doesn't have a true, you can't mark it as true or you can't mark it as false. You could say, I go to the store, that would be a statement because you either go or you don't go. But like the command, go to the store, is not a logical statement. Now, we can combine statements, and we often do that if you do like a Google search or something. You'll often use words that connect statements together, like and, or not, when you're forming a search. And what happens is if it's true, a search is true if the element is part of that search. And so that's when you get back all of the results, because it would meet those requirements and be true. Now, those and, or, and not words form the basis of something called Boolean logic, which is the process of combining multiple statements, like we just wrote above, that are either true or false, into a larger expression that could be true or false. So we could create something a little more complicated using those words. So you should do that first. I'm going to just put together the two statements I wrote already. So we have the sky is blue, and let's say I don't go to the store. So I've used both the words and then I also put the not by saying don't. So what happens with mathematicians is we don't like to write lots of words all the time. And so we come up with symbols to kind of have a shorthand for what we're talking about. And so the symbols that we're going to use in this logic section is going to be this kind of pointed up arrow, and that's going to be used for and. We're going to use the V looking shape for or, and the little kind of squiggle for not. Now, those should look kind of familiar if we kind of imagine them more curvy. If we go back to what we learned with sets, if we have that upside down U, that was the intersection. Remember, that meant that we were in A and we were in B. And so you can see that kind of similarity. For the union that we saw with sets, remember that meant you're either in A or you're in B. Again, we have that similar notation, but it's just a little bit pointy when we're talking about logic. And then similar, but again, the notation not exactly the same. But remember, the complement meant that we were not in A. And so we have a similar thing with that in logic, but we used that squiggle. And so for this next section, I'm going to ask that you complete a little matching game. So you could have clicked on that link or clicked on that link on our Canvas page. And when you do, it's going to have a bunch of statements and these symbolic form of the statements as well. So when you click on that link, it has all of these, again, these statements, and written both as regular English sentences and then also in their symbolic form. So you're going to cut those out and then try and match. It's not a match like right next to each other. You're going to have to cut them out and then rearrange them. So once you've rearranged them, then you can kind of check back here if it matches up. Now, one thing that we do want to do is write what the simple statements are and kind of basically defining what our P, Q, and R are. And so the P and Q, that's what this notation means again, is that I like cats and dogs And so our P would be the statement, I like cats. And Q would be the statement, really, I like dogs. Don't just write dogs here, right? I like dogs. That would be a complete statement there, like a complete sentence, basically. For these, we have that little squiggle. Remember, that means not. So not P and not Q. That matched up with cats are not reptiles. And neither, which is another way to say that they're not reptiles, are dogs. So we would say that the statement P is that cats are reptiles. It's just been negated. That's how we have that not there. And then our Q would be dogs are reptiles. Again, we have that negation, so we know that we're going to have to say that they are for our statements. For this next one, we have P or not Q. So that would match up with the statement, we have pancakes, or we will not have waffles. Okay, and I'm going to complete the rest of these really quick, and you could just check them. Okay, so you should take a look and check that you have the same statements matching up with that symbolic logic. You could pause it, double check, and make sure that you wrote all the statements, the individual simple statements for each P, Q, and sometimes the R's. All right, we're going to move on to these things called quantifiers. There are both universal and existential quantifiers. Universal are when they talk about an entire set having a certain quality or characteristic. So you say like, all people like classical music, or every person drives a car. Or you could say something like, no one eats spaghetti. All of those things are considered universal quantifiers. So an existential quantifier talks about at least one element in the set. So exist, like one exists. It uses words like some, one, and at least one. So let's suppose that your friend says one of these following statements. We want to think about what the minimum amount of evidence you would need to prove your friend wrong. So it says that everybody cheats on their taxes. So you can see that that is a universal quantifier here with that word everybody. So you should be able to determine what evidence you would need to prove your friend wrong for that one. And really what you need is just to show that not everybody would mean that there is one person that doesn't cheat, because then you can't say everybody. And then for the next one, it says one of these 6 cartons of milk is leaking. So for this one, we have one. That's an existential quantifier. And so if we want to prove our friend wrong, well, it says one of them's leaking. So what if we just said no one? So none of them. And you can see what ended up happening here is that we went from a universal quantifier, everybody, to an existential one when we were kind of coming up with the opposition to that statement. And when we had an existential, the hard word to say there, we would come up with a universal quantifier when we were trying to refute them. And you can see down below, in general, what's happening every single time is that for these negations of quantified statements, if you have an all or none, then what's going to happen is its negation will say at least one. So it will be existential. If you start with a statement of saying at least one, then its negation will say none or all. And so in general, we could say what's happening is that when we have a universal quantifier, we get a statement with an existential quantifier and vice versa. So for exercise number 3, I want you to take a couple minutes and try and come up with some statements that would make these given statements true. So these statement forms, I'm sorry. So I've written down some statements that are true and follow those statement forms. And so we have all humans are mammals, at least one student did the homework, no humans are trees, and at least one teacher is not here. So your statements that you created should be different than mine, but you can kind of use mine for example. And so for part 4, what we want to do is negate each of those statements that we created. And so when we look at our all A are B, if we want to negate the statement that all humans are mammals, all we really have to say is that at least one human is not a mammal, which you could see is a false statement, since again we chose these all to be true statements. For the next one, we're looking at least one A is B. So if we want to negate that, we're going to say no students did the homework. Again, if we knew at least one student did do the homework, then we know that this would end up being false. Next, we have no A are B. So to negate no humans are trees, we're going to say at least one human is a tree, which we know is false. And then the last one, at least one A is not B. So you got cut off there. We want to negate at least one teacher is not here, and so we can just say all teachers are here. And so that's all we have so far for logic part 1.